All right, plan for today. Let's finish up 8.3. After that, we're not going to try to do anything else. Okay, because I can't give you a test or quiz after today. And this will finish chapter 8. And our exam is done. And probably everyone has a million other things that they need to have some time to work on. So I think that's probably the plan. Cool? All right. Let's finish her up here. So we had been talking in chapter 8 about probabilities. Specifically in 8.3, we'd been talking about conditional probability. So what's the probability that B occurs given that some event A has already occurred? So the notation we use for that is this one right here. So if you have two dependent events and you want to find the probability that A and B occur, where A depends, or the B depends on A, you can do the probability of A times the probability of B given that A has already occurred. So say we're talking about the probability of that you're drawing names from a hat. There's 10 names in the hat. If I ask what's the probability of drawing your name and then your friend's name, it'll be 1 out of 10 times 1 out of 9. So the probability of drawing your name is 1 out of 10. That's independent of anything. The one drawing your friend's name was dependent on already one name removing, so the probability there is like 1 over 9. Does that feel okay? So as an aside, this is just a rearrangement of our conditional probability formula. We just multiply both sides by P of A. Not too crazy here. So when we're dealing with these conditional probabilities, this can become kind of confusing because there's a lot of possibilities to deal with. Oftentimes constructing something called a tree diagram is a useful way to kind of visually organize what's happening. So we're saying consider flipping a coin twice. We want the probability of getting 2 heads. Well, the first toss, I have a 1/2 probability of getting a head and the 1/2 probability of getting tails. And then from the heads toss, I have a 1/2 probability on my second toss of getting heads, or 1/2 probability of getting tails. And from the tails outcome, again, we have on the second toss a 1/2 probability of getting head and a 1/2 for tail. So if I want the probability of 2 heads, I'm looking at just this branch of my tree. So it'd be 1/2 times 1/2, which is 1/4. Let's say the probability of getting just 1 head total. So you could have this outcome where you got a head and then a tail, and you have this outcome where you got a tail and then a head. Everybody agree? So this path, the probability is 1/2 times 1/2. This path, the probability is 1/2 times 1/2. You take those 2 branches and you add them together. Everybody's okay with that? Let's look at another example. This says the Pew Internet and American Life Project finds that 93% of teenagers use the internet, and that 55% of online teens have posted a profile on a social networking site. This must be rather old. I expect way more than 55%. What percent of teens are online and have posted a profile? So again, I'm going to draw a tree diagram to represent this sample space. So I have some random teenager. 0.93 is online. 0.07 is not. Of those that are online, 0.55 has a profile. 0.45 do not. Those that are not online, 0 of them can have a profile, because it's, if you're not online, how are you going to have a social media profile? And then 1 would not. So that's a certainty. So if I'm looking for online and have a profile, I'm looking at this branch of my tree. So that should be 0.93 times 0.55. Everybody's okay with that? Okay. Let's do another example. In an experiment, researchers place 6 green toys and 4 red toys into a container. A child is asked to select 2 toys at random. What is the probability that the child chooses 2 red toys? Hi, Aiden. Hello. So again, start with the tree diagram. So first choice is red or green. What would the probability for red be? 0.4, 4 out of 10. And then green would be 0.6 or 6 out of 10, right? Our second choice then, what would the probability for red be this time? So we've already chosen 1 red toy out of the pool. So it would be now 3 out of 9. The probability for green, well, there's still 4 green toys there, but now there's only 9 toys total, so it should be 4 out of 9. Everybody's okay with that? And then down here, the probability for red, well, we've removed 1 green toy, but no red toys, so still 4 red toys in there, but there's only 9 total toys, so 4 out of 9. And then green, we've removed a green toy, so now there's only 5 green toys left and 9 total toys, so that one should be 5 out of 9. Is everybody okay with kind of how we talk through that? Again, very much common sense, but you have to understand kind of what's going on, right? I think the tree helps visualize what's going on so you don't miss any possible events. And it gives you a place like, okay, I just need to label some stuff, and you can see clearly what's happening before. Just an effective organization tool. Okay, so we did this. Again, all of these answers are fine because they all represent a number between 0 and 1. So whether you left it as an unreduced fraction, reduced fraction, a decimal approximation, or a percentage, all of those representations are fine. They all say the same thing. I like the fraction, if I'm given fraction. Okay, a survey for 1,000 people was performed regarding their gender and whether they were colorblind. The results are summarized below. What is the probability that a randomly person chosen at random is colorblind, given that the person is female? When you hear given that blah, 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 this is a conditional probability, right? So this is like, if we say C is colorblind and G is gender, let's use F for female or whatever. This would be the probability of C given F, right? The conditional probability formula says that should be the probability of
Boring.
Thank you. C and F.
What was that?
It was Matt, the custodian. So if I look at the table, what is the number of people that are colorblind and female? 2. And then I should divide that by the probability of the given. So how many people are female? 490. So this should be that. So 2 out of 490. Notice that I didn't really worry about the total. When I did this, I just did the number over the number. Because if the total's the same for both of these, then it just kind of cancels out and you don't have to really worry about it. So far, so good? Okay. The probability the person chosen at random is a colorblind female. Is this a conditional probability? No, because there doesn't say anything given that blah, 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 blah. So this is just the probability of C and F. So how many colorblind females do we have? How many total people do we have? So 2 out of 1,000. Now here we did it with a conditional I don't know why we did it that way. Okay. What is the probability the person chosen at random is a colorblind individual? So how many colorblind people do we have? How many total people? 42 out of 1,000. Everybody's okay there? All right. Next example. The probability that a regularly scheduled flight departs on time is 0.83. The probability that it arrives on time is 0.92. And the probability that it arrives and departs on time is 0.78. Find the probability that a flight arrives on time given that it departed on time. So we are looking for the probability of A given D. Everybody agree? My conditional probability formula is the probability of A and D, which were given in the problem, divided by the probability of D, which were given in the problem. So I just stack them up, plug them in, and there we go. Does that feel good? The flight departs on time given that it arrived on time. So this would be the probability of D given A. So again, conditional probability formula, P of A and D, we have, divided by P of A, which we have. Plug them into the formula. Is everybody okay? Hardest part about this is typically decoding what I have and what turning it into a formula, right? So you know what to plug in where. Okay. So let's talk about conditional probability alongside independence. Again, we say that two things are independent when the outcome of the first event has no impact on the probability for the outcome of the second event. So like if I flip a coin 2 times in a row, the first flip doesn't impact the second flip. But if I draw 2 cards out of a deck of cards without putting the first one back, me removing the first card changes the probability for the second card, right? The coin flip is independent. The card draw is dependent. Everybody's okay with that? So if two things are independent, the conditional probability, so the probability of A given B, if B has no impact on A, well, then it should just be the probability of A. The probability of B given A, well, if A has no impact on B, should just be the probability of B. Everybody agree with that? So if events are independent, your conditional probability just transforms into a regular probability, which should hopefully make sense, right? So if we have independent events, then my multiplication rule, instead of the probability of A times the probability of B given A, just as the probability of A times the probability of B. Right? If I flip a coin 2 times in a row, the probability of getting heads twice is a half times a half. Everybody's okay with that? You know, the probability of drawing 2 7s in a row is 4 out of 52 times 3 out of 51. Everybody's okay? One is independent, the other is dependent. All right. Let's go back to this example here. So it's the same airplane flights thing. Are the events arriving on time and departing on time independent? What would we need to do to check that? You could do it a couple of different ways. So one way you could do it is you could check to see if the probability of A is the same as the probability of A given D. Right? Because that's our definition of independent. So before we calculated the probability of A to be 0.92, or that we're given that, and we calculated the probability of A given D to be 0.94. So what can we say? They're not independent, right? Because the probabilities are not equal. Okay. The other way you could check this is you could check the departure, right? Is the probability of departure equal the probability of departing on time given you arrived on time? Again, P of D we're given. Probability of D given A we calculated earlier. We again notice not exactly the same. Say they're independent. Third way is we can look at, is the probability of A and D equal to the probability of A times the probability of D? And we have all of those numbers in our problem. And we notice that, nope, they do not match. Again, concluding that they're not independent. It's a third method, right? So again, the three methods to check for independence. You can check, is the conditional probability equal to the regular probability for either of the two conditions? Or you can check, does the multiplication principle hold for independence? P of A and B equals P of A times P of B. All right, in a certain country, the police stop drivers on suspicion of drunk driving. When stopped, the drivers are either given a breath test, a blood test, or both, or neither. Records show that 81% of drivers are given breath test, 40% given blood test, 25% given both. What is the probability that a driver is given a test? let's draw a Venn diagram here to kind of represent this, because a lot of this it said we can overlap, right? So I have my blood test, my breath test, and then both would be the intersection of the two. So if I know that the both is 0.25 and 40% are blood, but we're counting 0.25 of them there, we know that blood only is 0.15. Similarly, we can say that breath only is 0.56. And if I take the difference of the sum of these three minus 1, that'll tell us the neithers are 0.04. So what would our probability that we're given a test would be 0.15 plus 0.25 plus 0.56. Or you could use the addition rule, and you make sure you subtract the intersection so that you're not counting it twice. Is everybody okay with that? Again, I think it's much easier if you're going to draw the Venn diagram. I'm just going to add up the Venn diagram, but whatever. All right. Part B says, what is the probability that the driver is given exactly one test? So that would be blood only or breath only. So 0.15 and 0.56. I'll just add those together. So far, so good. The probability of given no test is yep. Again, you could do it as a complement, or you can just read it off your Venn diagram. I think if you're going to go through the trouble of reading the Venn diagram, I'm done using formulas. That's me personally, because it just, what are we doing here? Are the events breath test and blood test independent? So I would use the multiplication check for this. So I want to see if P of breath and blood is equal to P of blood times P of breath. Everybody's okay with that? Now we know what this is. What is the probability of breath and blood? It's on your Venn diagram. 0.25. The probability for breath, it's 0.81, and the probability for blood is 0.4. It's not blood only and breath only, it's all of it, right? And what do we get? Not 0.25. What do we conclude? Not independent. Everybody feel okay on how we did that? Again, the check is pretty easy. Let's look at a geometric probability situation here. The radius of the board, it looks like some kind of darts game, is 40 centimeters and is divided into 3 regions. You score 2 if you hit the center. You score 1 if you hit the white middle region, and 0 for the outside region. Everybody's okay with the game? Looks like darts to me. What is the probability of scoring a 2 in one attempt? What would be the area of the green circle divided by the area of the entire circle, right? Everybody agree with that? How do you find the area of a circle? Excellent. So what's the area for the green circle then? Pi times 10 squared, or 100 pi, or about 314. Everybody's okay there? How do we get the area for the red circle? Pi times 40 squared. We want the whole board, right? It's divided by the sample space. So pi divided by 40 squared. So you get 1 out of 16. When you reduce that sucker down. Everybody okay on that one? How about the probability of scoring a 1 in one attempt? That's going to be the area of the 1 divided by the whole area of the board. Everybody agree with that? How do you find the area of this donut-shaped one or white circle or white donut here?
Add the radius from the 2. Let's subtract it.
Yeah, so we'll find the area of the white as if it was a whole circle. So the radius there is 10 plus 10. So it'd be pi times 20 squared. But then we have to subtract out the 2 circle. So minus pi times 10 squared. And then the whole circle is still pi times 40 squared. So the area of the 1 was pi 20 squared minus pi 10 squared. Plug it into that area formula, or plug it in, blah, 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 3 out of 16. Everybody's okay? Okay. Sure. We're going to look at some now at least and at most questions. So in at least or at most questions, oftentimes you want to ask yourself, like, is it going to be easier to calculate specifically like at least 5 if that meant like adding up P of 5 and then P of 6 and then P of 7 and then P of 8 and P of 9 and P of 10 and P of 11 and P of 12? Or would it be easier to do 1 minus less than 5, where it'd be P of 4, P of 3, P of 2, P of 1, P of 0, right? So that's the question you want to be asking yourself on an at least question is, will it be faster to do it directly, or would it be faster to do it with a complement? Does that make sense? Usually you can do it either way. The goal is to hopefully not have to do like, I have to calculate 56 probabilities instead of 4. All right. Suppose the probability of there being rain on a given day is independent of there being rain on the previous day or the day before or after. Over the next 4 days, you determine the probability that it will rain on any one of the given days is 30%. What's the probability of it raining on day 1 and day 2? So all we care about is day 1 and day 2. We don't care what happens on days 3 and 4, correct? So if it rains those days or doesn't rain those days, that's fine. So all we care about is the probability of rain and then rain again. So that's just going to be the probability of rain on day 1 times the probability of rain on day 2. Because these are independent events, it told us that in the problem, I don't have to do a conditional probability for the second day. Is everybody okay? So just 0.3 times 0.3. Easy enough. What is the probability of it raining on day 1 or day 2? So that would be a union problem, right? The union symbol is for an or for sets. And I remember the probability formula for a union is P of A union B is P of A plus P of B minus P of A and B, because we don't want to count that intersection twice. That's what I'm going to do here. So I'm going to have P of rain on day 1 plus P of rain on day 2 minus P of rain on both days. It's convenient because what did I calculate in part A? The probability for both days, right? Rain on both days. So I can apply that here in this formula. So 51% chance it rains on one of the 2 days. So what is the probability of not raining on any one day? So it could be, let's think about what this would count then. So maybe it doesn't rain day 1, but it rains on day 2 and then 3 and 4. But it could not rain on day 1 and then rain on day 2, not rain on day 3, rain on day 4. Could not rain on day 1, could not rain on day 2, but then rains on day 3. And you see that if we try to count this out, there's going to be like a ton of possibilities here, right? This screams, please use a complement to do me. So what we want to do instead is calculate the probability that rains every day. And we'll just do 1 minus that. Because if we take out the probability it rains every day, then at least one of those days, we're not going to have rain. Everybody's okay with that? The probability of it raining at least once.
It's not 30.
At least once is a lot of different possibilities. Could be raining exactly 1 day and then no rain, or exactly 2 days and then 2 no rain, exactly 3 days and 1 day no rain, raining all 4 days. Yuck, right? What are we going to use? A complement. Yeah. So we're going to do 1 minus the probability raining on no days. Oh yeah, okay. And then I reiterate to okay, raining exactly 1 day, there's actually 4 possibilities here of how that could happen. And we get that's going to be really time consuming. So at least is greater than or equal to. So the complement would be strict less than. Less than 1 would be not raining at all. So that's what we're going to do. Do 1 minus the probability it doesn't rain. So probability of no rain times probability of no rain times probability of no rain times probability of no rain. Again, raining was independent. What's the probability it doesn't rain on a given day? Well, if it rains, it's 0.3, not raining would be 0.7. So I got that. And then I do 1 minus that number. And there we go. 76% chance of it raining at least one of the 4 days. Pack your umbrella. Ha ha ha. All right. What is the probability of it raining at most 3 times? What does at most mean? Means less than or equal to 3. So that means you could rain 0 times, 1 time, 2 times, or 3 times. Or we could use a complement here and do 1 minus it rains 4 times. I think I'll do the complement. That's going to be a lot less to calculate. So we just did this. So raining 3 times, or all 4 days is 0.3 times 0.3, there's 3. And then there's our complement. Guess what? That was the last slide. Yay! Thank heavens. All right, let's burn through these questions here. And we'll pack it in for the semester. I'm busting out my random student generator. So hold on to your butts here.
But I don't know the things. Yeah.
Sure.
Look at the newer stuff.
And I did the same thing.
All right, first up, 1A is Elise.
You want like a percentage?
Or just tell me how to get the, you can represent the probabilities of fractions, seems more appropriate in this problem.
So would be 221 over 310.
Nope. So you're close. Did you recognize it's a conditional probability? Because it says if we know the person owns a home, that's our condition, right? So the conditional probability is graduate given that they own a home. So the probability should be P of graduate and homeowner, 221, divided by homeowners. So how many total homeowners do you have? 340, right? Homeowner is
Sorry.
340. So it should be 221 over 340.
40.
Is that okay? All right. I need to do something with that. All right. Matthew, you're next. Part B. Oh, he's in the bathroom. Stay of execution for Matthew. We'll just get the next one when he comes back. It'll be fun. Christian, part B.
So we take the number of high school graduates, like total. Could you do something like that?
Again, you should read this and says if the person is a high school graduate, what's the probability that they also own a home? That's a conditional probability, right? So it's the probability homeowner given that they're a graduate. So the conditional probability formula would be the probability of graduate and homeowner. How many of those are there? Divided by the probability that you're a graduate. How many of those are? 310. So that should be your answer. 221 over 310. That feel good? Okay. Lexi, you're next.
So let's see. 0. The ones in the landline, is it the total? So 0.
Good. So 0.51 over 0.6. That's what you said, right?
That's not what I thought it was, but if I got it right, it works.
So again, this is a conditional probability question
Yeah.
because it's, you have a landline and also a cell phone. So given that you have a landline, do you have a cell phone? So it's probability of cell phone given landline.
Okay.
So the intersection, cell phone and landline is 0.51. And your total landlines is 0.6. So 0.51 divided by 0.6. Or 51 out of 60. Everybody okay? Aiden, you're up here for number 3.
Under 5%. Less than 1%.
You should be able to come up with a number. So you're trying to calculate the probability of high school athlete and collegiate athlete, right? So that's a multiplication rule. So that's going to be the probability of high school athlete times the probability of collegiate athlete given that they're a high school athlete. Everybody agree? That was our formula. What's the probability you're a high school athlete? .55, right? 55%. What's the probability you're a collegiate athlete given that you're a high school athlete? 5%, 0.05. So I'm just going to do 0.55 times 0.05. And I get, .0275, I think, or something. You do that. Does that make sense? So again, when we're doing these, think about your formulas. I like to try to start by like writing this symbolically. Like, what is it being asked to do? Like P of, this thing and this thing, P of this thing given this thing. Like, what am I trying to calculate here? Matthew, your name came up when you're in the bathroom, so you're gonna get this one. We're gonna do part A together. Shannon hits the snooze bar and alarm clock 60% on school days. If she doesn't hit her snooze bar, there's a 90% probability she makes it to class on time. However, if she hits her snooze bar, there's only a 0.7 probability that she makes it to class on time. We're going to draw a tree diagram to represent that. So what's the first decision or the first thing that's happening here? Right, but I mean for Shannon's decisions or whatever. Okay, so we have either snooze or no snooze, right? And you said 60% we do snooze, so what do we do for no snooze? Okay, great. And then what can happen after that? Okay, so we'll say on time and then late. You said that was 0.9. So what's the late possibility? Okay. And then if we do hit the snooze bar, okay, so the late is good. Feel okay? Everybody's okay with how we built that? All right, let's see, who's next? Luke. On a random day, what is the probability that Shannon is late for class? Okay. So there's two routes to late, correct? So there's this route. What's the probability on that route? So 0.6 times 0.3. And then this route to late. How do I calculate that route? 0.4 times 0.1. And then I add the two together. So I think it's 22% or something. Nope. I think it's 22, I said. So 0.6 times 0.3 plus 0.4 times 0.1. It's okay. We'll get it figured out.
Doing good up until
Yeah.
example 4. Oh, bro, I was
Isaac, part C.
Well, we just did that.
No, it's related. So this is a conditional probability, is what you need to recognize. So it's the probability that we hit the snooze given that we were late. So how do we calculate that conditional probability? Give me the formula.
It's like you probably which is like is 7.3 times 1.
It's what we just did. So it's that path is the probability that we hit the snooze and we were late.
Like 0.2.
0.6 times 0.3 is 0.18. And then whatever, that's a probability. That's good enough. You make it a decimal if you want, but you know, we don't need to be that fancy in here. Diego, you're going to help me draw the tree for this complicated looking thing that has like a whole paragraph.
So, assuming 3 options at the start.
Mm-hmm. Yep.
Lightning and
Great.
let's put the percentages.
Please.
0.74.
0.74.
No. Yeah, 0.17.
Okay.
Yeah, 0.62 and 0.21.
Okay. And then what's the other thing that happens then?
Like good grades and
Or not good? I'll just do that. Sounds good. Okay.
so 0.74 for the light. Yeah.
So the not good would be, okay.
68% moderate
Okay.
and 52%.
Well, you gotta give me the other one.
Oh, sorry.
That's our tree diagram. Who do you think is going to be next? There's not that many of us left. Zach, part B. Find the probability that this randomly chosen person describes his or her grades as good. So you're going to be using the tree diagram. How many paths get us to a G at the end? I think if you look a little harder, there's 3 paths, right?
Yeah.
Okay, what's the probability along the first path? Just multiply the 2 probabilities. And then we add, so what's the probability for the second path? Great. And then for the third path? Great. So that's what you do. Everybody okay? So you have to add. If there's multiple different outcomes, we're going to be adding. To find the probability for a given outcome, though, you multiply along, consecutive events. All right. Who's going to be next? Let's Roll those dice. Katie is still on my list. I need to update that. Gavin.
She got us one.
I think she withdrew. Part C. She's not on my roster anymore. That's what I know.
Probably third spot.
It's a conditional probability, right? Probability you're a heavy media user given you have good grades. So probability that you're a heavy user and have good grades divided by the probability you have good grades. So this we have, right? How do I do probability of H and G? Just that path, right? That's H and then G. Does that feel okay? We're going to need some practice on this, guys. I can't wait. Who's going to get this one? Aiden. Wait a minute. How come Lucas hasn't gone? That's weird. Where's my... you might not be in the roster or something.
Maybe, he gets all.
We can do it next class. It's like the next 10.
I think maybe the rest
Next class, maybe we can fix that.
Yeah, I'm going to have to look that up. I don't remember. I don't know. I don't remember where that source file is, but I'm going to look it up. Yeah. Because here's my code. It told me it reloaded because I got to the end. It said reloading. So
I feel like I had something from that. I really do feel like I have.
let's look.
Put his name in there twice.
Well, I can't do it here. I have to add it to the CSV file. Yeah, not in there, Lucas.
Yeah, you gotta give him the next 10.
Yeah, you're going to do this next one. So we get to draw some massive Venn diagram, it looks like. Great, I agree. Let's call those circles S for saxophone, T for trumpet, and D for drum. Saxophone.
So we put 2 in the middle.
Yeah.
In the middle.
The triple intersection, good.
For saxophone and trumpet, is 3. 35. No, it's 3. I think it's 3.
It's 5 because it says, but not all 3.
Oh, okay. 5, yeah. 1 for saxophone and drums, and 3 for trumpet.
Okay.
For trumpet,
For trumpet only
yeah,
is the spot that we're filling in.
we do
Good.
drums.
Whatever they do.
9. 10.
Still one more spot.
Does it all add up?
10, 15, 27, 30, 32, 33, 42. That gets us 8 leftovers. All right. Keep going, Lucas. Sure. The probability that a randomly selected person plays either the trumpet or the saxophone. Right, that's trumpet or saxophone, correct?
Add all that up.
Mm-hmm. Correct. So it's that 15, 27, 32, 33. 33. Okay, keep going. Plays the, what's the probability that a randomly selected person plays the trumpet given that they do not play the drums?
No. Something over drums. Something over 15.
So not drums would be all of this. So 8, 20, 35. And then trumpet and not drums would be that stuff, right?
And this is not a short pass.
So 12, 15, 24 that are some kind of instrument but not a saxophone.
You know, class is out, right?
Nope.
Oh.
Not even.
No bell?